Water waves are interesting because this first view is water in drop cables. So as we're looking at our tools, we can do a couple of things. I can look at multiple devices inside of the single premise and say, do they all have the same response? If yes, now I've connected that to the drop, right? Because it's likely that that water didn't intrude into the house and get into the splitter in the basement. So it's probably a squirrel chew or a tree rub or a staple, or, you know, sometimes when you're peeling the messenger off, you may peel some of the jacket of the cable and expose some of the braid and allow water to get in. Either way, it could be a loose connector and it, you know, dripped off the tap and got in the connector and transitioned down to the cable or migrated into the cable. Now, that water will lay in the cable in certain places, like low spots, or, you know, places where the braid and the outer jacket are cladded really well and the water can't pass by it. So the water will lay in a pool and it'll create these attenuation spots, where the attenuation at that part of the drop is higher than it is at other parts of the drop. So it creates these attenuation nulls, like right here, where the attenuation is greater and affecting different frequencies differently. So we see that this is a non-periodic wave, so likely there's water migration that it got to a connector. The shielding integrity breach, that where the jacket or the braiding was damaged on the drop itself, is also an impedance mismatch. So we've got several things going on in this drop. Now, the good news is drops are relatively easy to replace. You either lay a temp on top of the ground or hang a new one. But the signatures themselves are actually very unique, depending on how much water is in it, how long it's been there, how long it's corroded, how much water is still in the drop. And we see this sometimes in real rainy areas or places that have rainy seasons, where during the rainy season, when the rain is falling, this doesn't show up right away, right? It takes time for that water to get into the drop and then migrate and then settle. And then a week or two after we have a big heavy rain, these things start popping up. Well, if we don't address them right away, eventually it'll start to minimize a little bit as some of that water evaporates out or it disperses, and it won't entirely go away, but it'll leave corrosion in its wake. And eventually the drop will need to be replaced. But when you learn to understand some of the key indicators of a water wave, they're pretty easy to identify. You can just look at it and go, yep, that's water. Need to go replace that drop. Now in the hardline cables, they're very similar, but they tend not to be as severe. You know, the coaxial cables and the feeder and the trunk tend to be bigger. The water may not pool as much in certain places. You'll still have the nulls, the high attenuation nulls, like these, where the attenuation is greater in some places than others. But now you'll start to see this same signature on multiple devices in multiple accounts, right? So you could have a damaged feeder or trunk cable are all showing these same signatures, that multiple devices, but additionally you can, you know, some of that spectrum to help identify individual premise issues and in conjunction with hardline water waves. Now, resonant peaks. These are frequency specific gain typically caused by grounding problems in amplifiers. So how often do you see a really weird response like this that we may think of as a standing wave, and you go out and you either throw your ladder up on the strand or you boom up and you start to, you know, torque on the amp a little bit and it goes away. Over time, amplifiers can, you know, warp if the module retainer screws in the module aren't tightened properly to the housing itself, or the bolts on the outside of the housing aren't also properly tightened. Over time, through heating and cooling and expansion and contraction of the module and the housing itself, can warp and cause these grounding problems inside the amplifiers, which will then manifest themselves as these resonant peaks. Now, depending on the size of the amplifier and the size of the grounding problem as to how the peaks themselves manifest. These are 4 different amplifiers that have different signatures of different resonant peak, but they're all caused by the same thing. Sometimes they can move or include a frequency specific notch like a suck out. But in most cases, when you see a signature similar to this, it is a resonant peak that is associated with an amplifier. So some of the tools can localize or signature match and say this cluster of devices in this neighborhood all share the same signature. And then you can start to trace that back through the architecture to something called an LCA, or a least common ancestor in the architecture, to say the one thing that these all have in common is this amplifier. Now the great news about that is you can just drive straight to that amplifier and tighten up the module retainer screws, check it for corrosion, and typically it goes away. But understanding what the particular signature response is can help you lead you right to an amplifier or a drop or a span of cable. Okay, next will be, high frequency roll off. Do you ever guys, when I was a young tech growing up, I heard little ones can't jump and big ones can't swim. Did you guys hear the same thing? Good, even the new guys are saying, yep, little ones can't jump and big ones can't swim. So ultimately what that means is the higher frequencies tend to be affected more prominently by water intrusion. And again, go back to that drop scenario where the water pools, that creates that high frequency or high attenuation null in the cable and creates a roll off or excessive loss at particular frequencies. So typically when you see this high end roll off, it's associated with water in a device, either in cable, but typically in a passive or an amplifier or something like that. The passive devices, unfortunately, are basically just water collection buckets, right? If the weather gaskets inside the housing and the mating to the plate aren't properly sealed or tightened, the water just gets in there and it pools. We've had a lot of, I think, debates as to whether shrink boot, not shrink boot, does the water migrate through the connectors and get into the passives and then lays in the passives and create situations like this. But when you see a frequency response like this, particularly on a group or cluster of devices within your intelligence tools, you know you're looking for water. The question is just where. Again, localize the devices to the architecture and then translate that back to a least common ancestor, and that's a great place to start. Now, the other half of that equation is little ones can't jump, meaning low frequencies have a difficult time in bridging any gaps or discontinuities in the center conductor. Oftentimes that's loose seizure screws, but a lot of time it's pullouts where if the hardline connector is not properly tightened, particularly in the winter, right? We go through this every winter. The first cold snap, you find the suck outs. The second cold snap, when it gets really cold, that's when the outages come, right? Because if we miss the suck out the first time, as the cable continues to contract, it's going to pull completely apart. And then you'll either lose power or you lose continuity between the center conductor and the mating mechanism. So little ones can't jump. Typically, if you see the low end, early on in my career, I didn't draw the distinction between the return path and the low end, right? So if you think about your sub band from 5 to 42, and then your downstream typically starts about 55. So the lowest amplitude of a suck out is going to be 55, but conversely, that same discontinuity extends to the upstream as well. So typically where you have a suck out, the devices past that will also have high transmit levels because of that same discontinuity. So on the downstream side, you'll see a pull out or a suck out or a low end roll off, but it's typically associated with high upstream transmit levels on those same devices. Because if you think about it, those two frequencies are right next to each other, or those two bands.